All right, so last time what we were doing was partial fractions. And this is for integrating rational functions. The techniques we have left are Weierstrass is also what he wants, because I think there's going to be something about Weierstrass substitution on this assignment. So for partial fraction decomposition, what are we doing? Steps to complete a partial fraction decomposition and integrating to integrate rational functions. This is what the idea of it is. Proper rational functions. All right, so one, make sure it's proper. Which is a of x over b of x is proper. That means that the degree of a of x is strictly less than the degree of the denominator. Two, once we've made it proper, we want to factor the denominator into linear and factors and irreducible quadratic. Factors. Three, what we're going to then do is once we've factored this, once we have a proper rational function and a factored denominator, we make our partial fraction guesses. So what are those partial fraction guesses? Those partial fraction guesses are one, essentially I'll put them in the main categories. If we have a 1 over x minus a to the n term, this implies we guess that we're going to have a over x minus a plus b over x minus a squared up to, I should put indexing a1, a2, up to an over x minus a to the n. That's our partial fraction guess for linear terms. For irreducible quadratics, if we have 1 over ax, let's put it like this. Once we complete the square, also we're going to have to do this in there. There's a little thing that they don't point out. But if we have already completed square, basically, then we're going to guess a1x plus b1 over x squared plus a squared, the 1 plus all the way up to anx plus bn. We linear over quadratic x squared plus a squared. And assuming they've already, in that form, they've already assumed that you've completed the square on this quadratic as well, which I'll get into in a couple of examples. Then once we've made these partial fraction guesses, what do we have to do? We have to find the unknowns. These constants. This is a linear n by n or k by k system. If the degree of b is k. So we can tell how big the system, how many unknowns we're going to have to find by the degree of the denominator as well. Once we've finally done this, I've made my function which is rational A over B. I've made it proper, so the degree of A is less than the degree of B. I factored B. Then once I've factored B, I make all my guesses for partial fractions. Then I have to find these coefficients. Then finally we integrate. And this is basically partial fraction decomposition. So let me find a couple of examples in here. Do that one too. Yeah, let's do this one. So I have to pick one that's not too bad. No, example. Compute the integral of -2x plus 4 over, oh, this one's already factored. So sometimes I'll give it that way, sometimes you don't. My list basically just goes through all the things that we really need to do in the most general case if it isn't factored. So we go through each step. So if I'm doing this, step one, is it proper? Yes, it is. 2, is b of x factored? Yes. 3, we have to make our guesses. So in our partial fraction guesses, I have a 1 over x minus 1 is going to imply I guess a over x minus 1. If I have a 1 over x squared plus 1, which is what I have, then we're going to guess bx plus c, just different coefficients over x squared plus 1 is my power. 4, now I have to solve, now you have to know what that means to get all of these guesses. What we're saying now is that -2x plus 4 over x minus 1 times x squared plus 1 is equal to a over x minus 1 plus bx plus c over x squared plus 1. Because I had one linear factor, I guess one linear term on the right hand side, and because I have one irreducible quadratic factor, I have one linear over quadratic term on the right hand side. And now we've stuck, the idea is we're going to try and integrate this thing, but now I don't have to have the two guys on the bottom. We split it to 2 individual integrals. So once I have that, that says that I need a common denominator. Once I get a common denominator, this says that -2x plus 4 over x minus 1 x squared plus 1 is equal to a over x minus 1. What's it missing? X squared plus 1. So I multiply by x squared plus 1 over x squared plus 1 plus bx plus c over x squared plus 1. What's this one missing? It's missing x minus 1 over x minus 1. Now I have a common denominator, so I can get rid of it on both sides. So what I do is I now ignore it on both sides. And we can focus on the numerator now will give us -2x plus 4 has to equal ax squared plus a plus bx squared plus bx minus or plus cx minus c. If that's true, then what we're going to get is because the degree of b is 3, I know that the degree, or I have 3 unknowns to find a, b, c, and that gives me a system which I match the coefficients. This is 0x squared plus or minus 2x plus 4. So we get in the first equation a plus b. I look at the squared ones. and I get that has to equal 0. If I look at the next coefficients, I have to look at the -2 guy, has to match this guy and this guy. So what am I going to get? I'm going to get, sorry, I should have a -b on here. This says -b plus c is equal to, what is it? -2. And then in the last equation, we're going to get a minus c is equal to 4. Therefore, solving this linear system, usually I'll make it, especially on exams, we'll make it sparse enough so that you don't need a bunch of linear algebra to solve this. But the first equation says negative a is equal to b. And then c is equal to a minus 4 from equation 3. And then we put that into the last equation. This says that a plus a minus 4 is equal to -2. The second equation. So this is coming from 1, this is coming from 3. So the idea with 3 equations is I use the first 2 equations to solve them both for a, then I put them into the third equation. Solving for a in this equation now gives me a is 1. Once I have that, I get my other coefficients. This says b is equal to -1, and then therefore c is equal to 3. Or sorry, 1 minus 4, which is -3. Therefore, what that tells us is -2x plus 4 over x minus 1 times x squared plus 1 is equal to 1 over x minus 1, and then minus x plus 3 over x squared plus 1. We have a negative in both terms. I just factored the negative out. Therefore, 5 we want to integrate finally. So this is the partial fraction decomposition game. Make sure it's proper. If it's not, use long division. Once it's proper, factor the denominator into linear terms and irreducible quadratics. Once I've done that, I make my partial fraction guesses. Then I have to use linear algebra or whatever else to solve and find those coefficients. Once I have the a's and b's and c's and whatever, then I can split. The idea was to take the left-hand side, which had them multiplied together as products, to the right-hand side form, which has them all as linear terms or irreducible quadratic terms individually, and now I can integrate them. So this says that the integral of -2x plus 4 over x minus 1 x squared plus 1 dx is equal to the integral of 1 over x minus 1 dx minus the integral of x plus 3 over x squared plus 1 dx. How do we solve this? Well, they should all be now, in this case, without a little bit more work. Sometimes you have to complete the square on the irreducible quadratic, and that'll be a little bit of extra work. But this time we have, this is the integral of 1 over x minus 1 dx minus the integral of x over x squared plus 1 dx minus 3 the integral of 1 over x squared plus 1 dx. So this one I'm going to have to use a substitution. I'm going to use w is equal to x squared plus 1. So 1/2 dw is equal to x dx. You don't have to do them all in one step. So this is equal to, the first one is the natural log of the absolute value of x minus 1. Again, technically I'm using the substitution, a baby linear substitution, which is w is x minus 1, so dw is dx, and then you just get integral of 1 over w. But that, so minus the integral of, what do I get? 1/2 1 over w dw, and then minus 3 arctan x plus c. Now the last one is going to be the natural log of the absolute value of x minus 1 minus 1/2 natural log of the absolute value of w. minus 3 arctan x plus c. And then w was x squared plus 1. So this is equal to the natural log of x minus 1 minus 1/2 the natural log of x squared plus 1 minus 3 arctan x plus c. You can combine the last guy if you really want, but it doesn't really matter to me, the natural logarithms guy. So this in its various forms is how we, and the various forms are the types of integrals that we get at the end. The worst case scenario is an irreducible quadratic of a power, and then this becomes a little bit more difficult. But other than that, this is the general idea of how we go through and solve partial fraction decomposition. Let me do one more. With one that had. I thought I had one. I'm just looking for, okay, I'll just make it up then. Example 2. Sometimes in the irreducible quadratic, we have to complete the square, so I should do at least one like that. What if I was going to do x squared plus x plus 1 dx, the integral of this? Now it's proper. I won't go through all the steps, but it's proper. I guess I will go through them. It's proper. 2, is it factored? Yes. And so 3, what do we have to do? We have to make our guesses. What's our guess? We're going to have 1 over x squared plus x plus 1 implies we're going to guess that we're going to get ax plus b over x squared plus x plus 1. Or that's not the right form of what we're doing. You'll see with the a and the b will become different. What we want to do this time is we want to complete the square on the irreducible quadratic and put it there. So x squared plus x plus 1. What does this equal? You'll see we don't have to, once we complete the square, we won't have to factor this or make any guesses either, because it will be in partial fraction form. It'll already be ready. If there was another linear term there, then we would have to split them out. But because there's only one term here, I can just complete the square. So I'm completing the square on this. I want the x term to go away. So I have a b is 1. I divide by 2. So b is 1. b over 2 is 1/2. b over 2 squared is equal to 1/4. So what's going to happen here is I'm going to have x squared plus x plus 1 over 4 minus 1 over 4 plus 1. This now is the completed square. That's why I did that. And so what I have left is I have x plus 1/2 squared plus 3 over 4. Is the moral of the story. So this integral 1 over x squared plus x plus 1 dx is equal to the integral of 1 over x plus 1/2 squared plus 3 over 4 dx. The first thing you can do at first, if you want to do this, is get rid of the shift. Now that I've completed the square, I'm going to let w equal x plus 1/2. So that says dw is equal to dx, and this integral will become the integral of 1 over w squared plus 3 over 4 dw. Now you can see that I didn't have to make any partial fraction guesses because I can integrate this thing. I'm going to get an arctan essentially, but this is equal to the integral of 1 over w squared plus root 3 over 2 squared dw. Now this is what I'm saying. we use arctan so often in partial fraction decomposition that you probably just want to memorize this formula. If I have 1 over w squared plus a squared, this is equal to, what is the antiderivative of this thing? 2 over root 3 arctan of 2w over root 3. It's 1 over a arctan w over a plus c. And then what was w? W was x plus 1/2, 2 over root 3 arctan. And then they cleverly put the 2, distribute the 2 in there. So there should be 2x plus 1 over root 3 plus c. Why did I get that? Because w is equal to x plus 1/2. We distribute it in there. So this is how I deal with irreducible quadratics. If I have an irreducible quadratic to a power, which I won't do on exams, so they don't have to worry for next week, then we use trigonometric integration. But for time-wise, what's the last one? I need the Weierstrass stress substitution. Trigonometric integrals. Or this is sometimes called universal substitution. So the idea is to transform integrals with rationals in sine and cosine rational expressions in sine x and cos x into partial fraction decomposition. In a variable t. So this is the goal. So basically what we have is, so as an example here, what if we want to integrate 1 over sine x plus cos x dx? If you're interested, the r of xy here, if I had 2 variables, would be 1 over x plus y. And therefore, it implies if I had a rational function in sine x and cos x of those 2 variables, it would be equal to 1 over sine x plus cos x. So that's how I know it's a rational function, a ratio of 2 polynomials, essentially, in not x and y now, not of 2 regular variables, but of sine x, cos x. So that's just what we're talking about, rational functions inside there. If I want to integrate this thing now, how am I supposed to integrate this thing? The clever idea is to use Weierstrass substitution and these clever trigonometric identities. So what we're going to do is we're going to let t, an inverse substitution, we're going to let t equal tan of x over 2. And why are we doing that? Well, first of all, we have, this says that tan x over 2 is equal to t over 1, which is opposite over adjacent. So if I put x over 2 down here as my angle, what that says is I should have t and a 1. That says that my hypotenuse is t squared plus 1. And now what we're going to use is that square root will go away. And yeah, no, I just put that in my notes because it's an extra term. I won't do Ostergatsky's method. That one's more confusing. It just is a more slick way of, if you did it regularly, it just gives you a way of breaking it down in a clever way, but there's no point in doing this. In my lecture notes, if you look, there's all kinds of weird special extra. I have about 20 different categories of substitutions you can use, etc. After trigonometric substitution, hyperbolic substitution, all of these ones. There's all these algebraic ones, but I just add these because I can't help myself, and I like to find and become more and more of an expert in all these integration techniques. So as soon as I find a new one, I pull them all in there and put them in the lecture notes. But for now, in a first introductory integration class like 115, it'll be the meat and potatoes. Substitution rule, integration by parts. Then we're going to do trigonometric integrals, trigonometric substitution, partial fraction decomposition, Weierstrass substitution, so that we can turn rational sine and cosine into partial fraction decomposition, and then that will be it. So this is our last technique. You won't need to know Ostergatsky's. And that's for partial fraction decomposition, not these ones. Now what we have in that scenario, though, is because of this, how do we use this to get rid of sine and cosine? What we cleverly have is that, first of all, we need our differential. So if that's what we have, then yeah. So if we have this, first of all, we have dt is equal to secant squared x over 2 times 1/2 by the chain rule. And so that says that, or sorry, dx. And so that says dx, the thing that we have and we're trying to get rid of, we have a dx in our integral and we need to get rid of it. So that is going to say that this is 2 cos squared x over 2 dt. But first of all, what we're going to want to do is find out what sine of x over 2 is and what cos of x over 2 is. So sine of, sine of x. Sine of x is equal to, first of all, if we look at this one, I'm trying to go through them all in one. If we look at cos of x over 2, this is equal to what? Cos is adjacent over hypotenuse, so 1 over the square root of t squared plus 1. So cos squared x over 2 is equal to 1 over t squared plus 1. So this says dx is equal to 2 over t squared plus 1 dt. Every time, so we can memorize these ones, I'm just show you every time how we can derive these things. So now we have its liquidation in x's. All x's must go in this substitution, but first of all, we had to get rid of the differential in reverse. So we find a way using the triangle to get rid of dx. Now we need to know what, we also have a sine x and a cos x. How are we going to get rid of those guys? For sine x and cos x, we see that sine x is equal to sine of 2 times x over 2. So we're going to use a double angle formulas. And that is equal to 2 sine x over 2 cos x over 2. And if we look at this, this is going to be 2 what's sine sine x over 2 is equal to t over the square root of t squared plus 1, and cos x over 2 we already saw is equal to 1 over the square root of x, or t squared plus 1. So if I put that in there, I'm going to get t over the square root of t squared plus 1 times 1 over the square root of t squared plus 1. So that says sine x is equal to 2t over t squared plus 1. What's cos x? Cos x is the same thing. This is cos 2 over x squared over 2, which is cos squared x over 2 minus sine squared x over 2, which is equal to, long story short, when we add this up, we're going to get cos x is equal to 1 minus t squared over 1 plus t squared. So in general, if we have this, if I have the integral of a rational function in sine x and cos x dx, this now turns into the integral of a rational function in what was sine x. We're going to have 2t over t squared plus 1. What was cos x? 1 minus t squared over 1 plus t squared. And then 2 over 1 plus t squared dt. And then because those two arguments are rational and the r guy is a rational function, all of this will be rational in t. So the idea was we've taken this rational function in sine and cosine, which I don't know how to integrate. I've used universal substitution or Weierstrass substitution, and I've created a rational function in t, and I can use partial fraction decomposition minus the Ostrogradski's method to do partial fraction decomposition on this. So with our example, we had the integral of 1 over sine x plus cos x dx. What that says is we know that this is going to be equal to, having done all the things that I just did, the integral of 1 over what is sine x, 2t over t squared plus 1 plus 1 minus t squared over t squared plus 1 times 2 over 1 plus t squared dt. That's just putting the substitution in. Once I've done the Weierstrass substitution and I clean this up, I'm going to get the integral of 1 plus t squared, getting a common denominator and then flipping it. And then what do I have? Negative t squared plus 2t plus 1. And then we have 2 over 1 plus t squared dt. So the good news is these two things canceled each other. And I get equals the integral of 2 over negative t plus 2t plus 1 dt. This is equal to, I have to complete the square and do a little bit of fudging, but this is the integral of 2 over 2 minus t minus 1 squared dt, which is, if I make a substitution now, I can make a baby substitution. W is going to equal t minus 1, and dw is equal to dt. This is equal to the integral of 2 over 2 minus u squared du. Nobody said it would look nice, but now I have to use partial fraction decomposition. This is equal to the integral of 2 over root 2 minus u root 2 plus u, or sorry, w, dw. Now what do we have to do? Because I have this, we have to make partial fraction guesses. So 2 over root 2 minus w root 2 plus w is equal to, what are we going to get? This is going to be a guess of, we have two linear terms, 1 over root 2 minus w plus b over root 2 plus w. We'll get two linear terms. And what we get from this is that, long story short, a minus b is 0, and root 2a plus b is equal to 2. And that says that A equals B equals 1 over root 2. I'm skipping the details of solving for the A's and the B's because I'm assuming hopefully that you set this up over and over again. You can try this, but that's the coefficients. So now I'm doing partial fraction decomposition. It's factored, it's proper. I make my guesses, I find my values, and this says that the integral of 2 over root 2 minus W root 2 plus W dW is equal to the 1 over root 2 integral of 1 minus root 2 minus W dW plus 1 over root 2 integral of this room root 2. Let me squeeze it in there, but it factors it into the two individual terms. Plus 1 over root 2, the integral of. Now that we've done that, what that does for us is this gives us two reasonable integrals now. This is 1 over root 2, the natural log of the absolute value of root 2 minus W, plus 1 over root 2, the natural log of root 2 plus W plus C. And so this gives us, putting all of our substitution back in, 1 over root 2, the natural log of the absolute value of root 2 plus 1 minus T. Remember what W was? W was T minus 1, or T minus 1, plus 1 over root 2, the natural log of the absolute value of root 2 plus 1, or sorry, T minus 1 plus C. And what was T? T was tan of x over 2, so this becomes 1 over root 2, the natural log of root 2 plus 1 minus tan of x over 2 plus 1 over root 2, the natural log of root 2 minus 1 plus tan x over 2 plus c. Nobody said it would look nice, but this is the idea of partial fraction decomposition once we have Weierstrass substitution. So Weierstrass substitution, again, what's the goal of Weierstrass substitution? The goal of Weierstrass substitution is to turn a rational function in sine and cosine, trigonometric functions, into a rational function in t, which it does. And then we have to use sometimes a baby substitution to make it look nicer. And on top of that, we have to use partial fraction decomposition to integrate the t variable and then put everything back into our x variable. So this is the most complicated one, but a lot of the time when we're doing this or doing natural sciences, we'll get an integral that has a rational function in sine and cosine, and it's like, how are we going to integrate this? So this is why Weierstrass substitution is the last substitution we do, basically, because now that we have all of these other ones, Weierstrass substitution turns rational in sine and cosine into rational in t, and then we can use partial fraction decomposition to integrate the t and then get back our variable. All right, and then, so I only have 10 minutes, but I should start it, and on Thursday, because it's on your homework, they have this improper integrals on your assignment. So the cutoff will be just the integration techniques and possibly the first couple kinds of improper integrals. I won't make you do the comparison on the midterm 2, but the cutoff will basically be the integration techniques and then improper integrals of type 1 for sure, maybe type 2, but type 1 and type 2. So there's improper integrals. And there's type 1 and type 2. Basically, type 1 has horizontal asymptote, and we have an infinite strip in this sense, and we want to know whether that the area under that infinite strip is finite or infinite. And then we have a type 2, which has a vertical asymptote for our function. And then we're trying to integrate the area inside there, and we want to know if that area inside there is finite or infinite. It's like, what are you talking about? So the type 1 and type 2 that we're going to talk about, I can just draw them and then show you the scenario of what we're trying to do here. So sometimes what we might have is a C value where if I'm trying to integrate from A to B, I'm trying to find out if I have a function now. I'm trying to find out whether the area from A to B is that area finite or infinite. But we have a discontinuity in there. So that's type B, and that's so division by zero somewhere in our expression. This would be, say, the integral from A to B of 1 over x minus c squared dx, something like this. So you're like, I don't see what the problem is. Well, the problem is we have division by zero at c, and c is inside that interval AB. So we want to know whether that area that we're going to compute under there is finite or infinite. Type 1's a little bit easier, and it's easier to see because what we're going to do is we're going to have an A in a lot of the cases, and then we have a function, say doing that. But we want to know now, is this area from A to infinity, is that area finite or infinite? So this is the idea of, pictorially, this is the idea of what we call improper integrals of type 1 and type 2. We have this either a horizontal asymptote we're approaching, and we want to know whether the area under that as it goes to infinity, if that area is finite or infinite for type 1. And for type 2, we have an infinite discontinuity or a vertical asymptote inside that interval, and we want to know if we approach there cleverly, can we have that this is going to be finite or infinite area, or the integral, and that's what we're going to call it. This one we would call the integral from A to infinity of f of x dx. Say you could call it 1 over x if you want. So this is the idea of improper integrals of type 1 and type 2. We want to know whether this is finite or infinite in both cases. So I'll do type 1. So basically, if I have a function f from A to infinity into R, and so if the integral from A to t of f of x dx exists for all t greater than or equal to a, then what we do is we define the integral from A to infinity of f of x dx is, by definition, the limit as t approaches infinity of the integral from A to t of f of x dx. And again, pictorially, what this is doing is, I always say, if you're doing limits and you're not picturing a function, the graph of a function, you're doing them wrong. What they're now doing horribly is, now that we've just given you all these integration techniques, we're going to say on top of that, we're going to make it more complicated, because now you're going to have to take a limit of the integral. And this is, so you're going to have to take the antiderivative, then you're going to have to keep all those limits on there. Then there's going to be L'Hopital's rule inside these integrals. So this is going to be why these are a nightmare at first. But pictorially, what we're saying is, in this scenario, we have a function, and then we have an a. And then what we're saying is, this guy, if we had t, a to t, that's definitely a finite area. We can compute that. That guy is just going to be the integral from a to t of f of x dx. And then what they're going to do is, they're pushing t to infinity. They're going to take the limit of that. And so if that exists for all of them, that's our definition of that improper integral will be the limit of those finite integrals. Otherwise, we say it's infinity. In such a case, we call the integral from a to infinity of f of x dx, which is less than infinity. If that happens, we call this convergent. If the improper integral from a to infinity of f of x dx is equal to infinity, we call this divergent. So that's what they're going to ask all the time. Is this convergent or divergent? What we mean is, does that area converge to a finite area, or is it just an infinite area underneath that infinite strip? Is the main idea. So example, the integral from a, let's do 1 to infinity of 1 over x dx versus the integral from 1 to infinity of 1 over x squared dx. And what we're asking is convergent or divergent for each one. So for the first one, we apply the definition. The integral from 1 to infinity of 1 over x dx is equal to, by definition, the limit as t approaches infinity of the integral from 1 to t. So what we're doing here is we're taking that improper integral on the top, and we're saying we're going to push t to infinity and then integrate all of those finite guys of 1 over x dx. So the first thing you do is get a limit of the integral of the finite ones. Now what I do is I ignore the limit for a second. I have to anti-differentiate that integral. So I have to find the integral of this, the limit as t approaches infinity of, what do I have? It should be the natural log of the absolute value of x evaluated from 1 to t by the fundamental theorem of calculus part 2, which is equal to the limit as t approaches infinity of log t minus log 1. Log of 1 is 0. So this becomes the limit as t approaches infinity of log t, which is infinity. So divergent, turns out. For the second one, if we do the integral from 1 to infinity of 1 over x squared dx, then what we have is this is equal to the limit as t approaches infinity of the integral from 1 to t of 1 over x squared dx. But now what's going to happen is I have the limit as t approaches infinity of, now I'm going to get negative 1 over x is the antiderivative of 1 over x squared evaluated from 1 to t, which is equal to the limit as t approaches infinity of 1 minus 1 over t, which is equal to, this one will go to 0 as t goes to infinity, which is 1, which is less than infinity, so convergent. The conclusion. So if you get a number and it's less than infinity, then we call this a convergent integral. When we get positive infinity, we get divergent, is what we call it. So this is the rough idea of improper integrals type 1 and type 2. There are some nuances. I'll go over them on Thursday, but for now, also Thursday will just be online for this week, and then I'll worry about and try to figure out for the rest of the semester what the heck we're doing or what I'm allowed to do. But hopefully we can just keep it online. I don't see any objections from my point of view. I don't see any objections from anyone else's point of view, but they may force us to do certain amount in class, but I'll push it at least to next week, and we'll do the midterm online as we did for the second one, so that we're not changing the status quo too much. So I will post everything also later today so that you have all of this, and I'll see you on Thursday.